Imagine reading this sentence, word by word. Your brain remembers what came before. But traditional neural networks? They can't do that. Every word is processed independently, with zero memory of what came before. This is a catastrophic problem for language. Because in text, context is everything. The bank was steep versus the bank was closed. Same word, completely different meanings. And the only way to know, remember what came earlier in the sentence. This isn't just a language problem. Stock prices, weather forecasts, music generation, video analysis. The world is full of sequential data. So how do we give neural networks memory? Enter recurrent neural networks. Let's understand the problem. Traditional feedforward neural networks are brilliant at many tasks. You give them an input, they process it through layers, and boom, you get an output. Perfect for images. Each pixel can be processed independently. The position of a pixel matters, but not the order. But text, totally different story. Let's try feeding a sentence through a feedforward network. The cat sat on the mat. The network sees the cat sat on the mat, but it processes them like random items in a bag. No memory, no context, no understanding that sat refers to cat or that the second that introduces mat. This fails catastrophically for translation, word order matters, sentiment analysis. Not bad is not equal to bad text generation. Gibberish without context speech recognition. Phonemes depend on neighbors. The longer the sequence, the worse it gets. The network has zero memory of what it saw 10 words ago, or even 2 words ago. We need a network that understands time. A network that can remember the past while processing the present. Here's the breakthrough. Recurrent neural networks add a loop. Instead of just processing input to output, an RNN maintains a hidden state, a memory that gets passed forward through time. Let me show you how this works. Step 1, we input the first word. The RNN processes it, updates its hidden state, its memory, and this memory is saved. Step 2, we input the second word. Cat, the RNN processes cat plus the memory from the, updates the hidden state again. Now the memory contains information about both words. Step 3, we input sat processes sat plus memory of the cat. The network now understands the context of the entire phrase. Mathematically, h sub t equals tan of w sub h times h sub t minus 1, plus w sub x times x sub t, plus b. The hidden state h sub t is a function of the previous hidden state h sub t minus 1, the MOR with the current input x sub t, the new WRDN learned weights w, how TO combine them. This creates a feedback loop. Information from the past influences the present, which influences the future. The bank was steep. Watch the hidden state evolve. That creates initial context. Bank could be financial or geographical. Was is a verb looking for description. Steep. It's a riverbank, not a financial institution. The memory disambiguates. The context built up through the sequence resolves the ambiguity. This simple idea unlocks machine translation, text generation, sentiment analysis, speech recognition, video captioning. All because the network can finally remember. RNNs sound perfect, right? Well, there's a critical flaw. The author, who was born in Paris and later moved to London where she attended university before eventually settling in New York, wrote bestsellers. What did the author write? Bestsellers. Who wrote them? The author. Where was she born? Paris. But watch what happens to the RNN's memory across this long sentence. During training, the network learns by backpropagation through time. But here's the problem. When we backpropagate through 20 plus time steps, the gradient, the learning signal, gets multiplied by small numbers over and over again. 0.9 times 0.9 times 0.9. 20 times equals 0.12. The gradient vanishes. It becomes so small that early time steps barely get any learning signal. This means the RNN forgets long-term dependencies that can't learn relationships between distant words. Struggles with sequences longer than 10 to 15 steps. The agreement, which was signed years ago, is RNN, what agreement? I forgot. He said he would 50 words later, come tomorrow. RNN. Who said what now? The vanishing gradient problem makes basic RNNs nearly useless for real-world language, where important context can be separated by dozens or hundreds of words. We needed a solution. And in 1997, we got one. Meet the Long Short-Term Memory Network, LSTM. Instead of a simple hidden state, LSTMs have a sophisticated cell state, a memory highway that information can flow along unchanged. LSTMs solve the vanishing gradient problem with gates, learnable filters that control information flow. 1. Forget gate. What should we throw away from memory? looks at the current input and previous hidden state, decides what to delete from the cell state. Example, after the bank was steep, we can forget the financial institution interpretation. 2. Input gate, what new information should we store? Decides which new information is important enough to add to long-term memory. Example, store that this is a riverbank, not a financial bank. 3. Cell state UPD, the old cell state is multiplied by forget gate, throwing away irrelevant info, added to new candidate values filtered by input gate. This creates a protected memory highway. 4. Output gate, what should we output based on our memory? Decides what parts of the cell state to reveal as the hidden state output. Here's the magic. The cell state provides a path where gradients can flow backward through time without vanishing. The author, who was born in Paris and later moved to London, where she attended university before eventually settling in New York, wrote bestsellers. LSTM cell state maintains author all the way through. Forget irrelevant details, Paris, London, New York. Remember subject, author. Connect to predicate, wrote bestsellers. LSTMs can handle sequences of 100 plus time steps, complex long-range dependencies, multiple interacting contexts. This breakthrough enabled Google Translate in 2016, speech recognition systems, music generation, handwriting recognition, video description. LSTMs dominated NLP from 1997 to 2017. In 2014, researchers asked, do we really need all those gates? Enter the GRU, gated recurrent unit. A simplified LSTM with just 2 gates instead of 3. 1. Reset gate. How much past information should we forget? Controls how much of the previous hidden state to ignore when computing the new candidate state. 2. Update gate. How much should we update with new information? Acts as both the forget and input gates. It's a trade-off. The more we keep from the past, the less we accept from the present. LSTM versus GRU. LSTM has 3 gates, separate cell state, more parameters, slightly better for very long sequences, but slower to train and more complex. GRU has 2 gates, single hidden state, fewer parameters, so faster training, often equal performance, but slightly worse on very long dependencies. In practice, GRUs perform almost identically to LSTMs on most tasks, but train 30% faster. Today's recommendation: start with GRU for faster iteration. Use LSTM if you need maximum performance. But honestly, both are being replaced by transformers, which we'll cover in the next video. Let's see RNNs, LSTMs, and GRUs in action. 1. Machine-to-on encoder-decoder architecture. Encoder LSTM reads source sentence. Decoder LSTM generates translation. Context vector passes information between them. 2. Text generation, once upon a time. LSTM predicts next word, feeds it back, generates entire stories. Shakespeare-trained models, code completion, chatbots. 3. Sentiment analysis, not bad. The LSTM remembers not and inverts the sentiment of bad. 4. Speech RNN audio waveform to LSTM to text transcription. Handles context. There versus there versus there. The evolution, 1997. LSTMs invented. 2014. GRUs introduced. 2015. Attention mechanisms added. 2017. Transformers replace RNNs. 2023. LLMs dominate. But RNNs still matter. They are foundational knowledge for understanding transformers. Still used in resource-constrained environments. Great for real-time streaming data. The stepping stone to modern AI. Remember, sequences need memory. RNNs provide loops. Vanishing gradients kill long-term memory. LSTMs use gates to maintain cell state. GRUs simplify with fewer gates. Both enabled the AI revolution. Next up, how attention mechanisms and transformers crushed sequential processing by processing everything in parallel. Subscribe and we'll see you in the next video.